Right, students, we are back with the Laurie-Bronsted concept. In the previous episode, we went with respect to the principle of Laurie-Bronsted, the proton transfer or proton exchange. I did talk about that. Now, I'll actually explain you how the proton transfer helps to recognize an acid with respect to its conjugate acid and a base with respect to its conjugate base. To make and to save some time, I have already given a few compounds. You can see I have listed them over here. And now we will accordingly find their conjugate acids and conjugate bases. There is a simple technique we can just keep in mind and get conjugate acids and conjugate bases of any DEM compound. Let's see how. First of all, I'll consider the conjugate acid of these following compounds. You can see a list of compounds I have stated over here. I am going to consider their conjugate acids of these compounds. Fine. So what is the concept to find the conjugate acid? Let's see. What is the compound over here is water. Now when you want a conjugate acid of any compound, any DEM compound, keep this in mind that you need to add a proton. Add means plus. A proton means H plus. Add a proton in any compound and that will give you its conjugate acid. Simple as it should be. H2O. Add a proton. What will convert? It will convert into H3O plus. Why? Because oxygen has the lone pairs and that will accept the proton which is lacking electron. So that is forming H3O plus. So what is the conjugate acid of water? If anyone is asking you, you can simply say that conjugate acid of water is H3O plus. Similarly, I am taking CH3COOH, acetic acid, and I want to find its conjugate acid. Simple. Add a proton as we did earlier. So it will convert into CH3 COO H2 because a proton is added. So H2 but with a plus sign. So I'll write H2 and I'll place a plus showing or indicating that it has been added with H plus. For CH3COO minus, try to understand very clearly. This is CH3COO minus. I am adding a proton H plus. 1 minus 1 plus gets nullified. So automatically the compound formed will be CH3COOH. So conjugate acid of acetate ion is acetic acid. I am taking hydroxide ion, that is OH minus, and I want to find its conjugate acid. I'll add a proton H plus into it, so it will convert straight away into water. So what is conjugate acid of hydroxide ion? That is water. Now I am taking O2 minus. No H on oxygen, but oxygen has got 2 minus charges. No problem. I'll add H with 1 plus. Now I have added a proton 1 plus and oxygen has got 2 minus. So 1 minus will be left intact and the compound formed will be OH with 1 minus sign. Again, HCO3 minus. I'll add a proton and that will convert into H2CO3. Carbonic acid H2CO3. Similarly, carbonate CO3 2 minus carbonate ion. I want its conjugate acid. What I'll do? I'll add a proton. But how much or how many charges in the minus form? 2. How many charges in the plus form? Only 1. So 1 plus 2 minus 1 more minus will be left intact and H will get added. So the compound will be HCO3 bicarbonate ion will be formed. So carbonate ion conjugate acid is bicarbonate ion. Again, HSO4 minus. I'll add a proton to it, H plus. 1 minus 1 plus nullifies and the compound formed is H2SO4. Simple. Similarly, I have SO4 2 minus, sulfate ion. I'll add 1 proton, H plus. So 1 minus will be left intact because there are 2 minus charges and the compound formed will be HSO4 with 1 minus charge. Again, H2PO4 minus. I'll add a proton to it, H plus. So what will be formed? H3PO4 4 will be formed. Again, HPO4 2 minus, I'll add a proton. So it will convert into H2PO4 with 1 minus charge. I'll take phosphate ion, PO4 3 minus. Add a proton. So it will convert into HPO4. But now instead of 3 minus, I'll have 2 minus charge. HF. Can we have a conjugate acid of HF? Little bit confused. No problem. See, fluorine is highly electronegative. It has got 3 lone pairs intact. And so obviously it can gain a proton when it is provided with. So if I provide a proton H plus to HF, it will definitely give conjugate acid. And that is what it forms is H2F. But then with a plus sign. Or you can show H plus over here, no problem. Removing from here, showing it or indicating that the proton is added to the compound. So that is how you can get conjugate acid for the following compounds. Similarly, if you have water and if someone asks you to find the conjugate base of water, you can? Yes, you can. Laurie-Bronsted theory concept is proton transfer or proton exchange. A compound which gains a proton is a base. Fine. So if H2O gains a proton, it can form H3O plus. Fine. It's gaining a proton and losing. That is the concept. Fine. Now here we have added a proton to get conjugate acid. Now here we will remove a proton to get conjugate base. So simple theory you keep in mind. Add a proton gives conjugate acid. Remove a proton minus proton will give you a conjugate base. So out of water molecule, if you remove H plus, what will be left is OH minus. So OH minus is conjugate base for water. H3O plus is conjugate acid for water. I have taken the same compounds just to make things more clear. Again, suppose if I take acetic acid and I want its conjugate base, what I'll do? Simple theory, remove a proton from the compound. There is a proton H. I'll remove it in the form of H plus. What I'll be left with is CH3 COO minus. So that will give me acetate ion. Now over here, acetate ion. I want its conjugate base. Interesting, and keep it in mind. Do we have H with respect to COH which can be ionized? We don't have. If you don't have a proton, means it in the form of hydrogen atom, how can you lose it? You can't lose it. So acetate ion, once again, please concentrate. Acetate ion cannot form or cannot give its conjugate base. Not possible. Not possible. If you think these are the 3 H atoms, no, they are not the 3 H atoms. As you can have H over here in the form of ionic charges, these are covalently bonded hydrogen atoms to the carbon, so they will not ionize. Fine. So not possible as far as acetate ion concerned. We'll take OH minus. I want to get its conjugate base. I can get it because there is H which can be eliminated, and so I'll have O raised to 2 minus. 1 minus charge adds because H plus is removed. For O2 minus, can I have the conjugate base? No, I can't, because there is no hydrogen present in the compound. For HCO3 minus, bicarbonate ion, yes, I can, because the H from bicarbonate can be eliminated. So that will give you CO3 2 minus. Again, for carbonate ion, CO3 2 minus, can I have conjugate base? No, I can't. So here it is not possible. For HSO4 minus, can I have conjugate base? Yes, I can, because H can be eliminated in the form of H plus, and if it gets eliminated, what I'll be left with is SO4 2 minus. What about sulfate ion? Can I have the conjugate base? I can't, because there is no H present which can be lost. For H2PO4 minus, yes, 2 H atoms are there, I can lose at least one, and that will convert into HPO4 2 minus. For HPO4 2 minus, can I have the conjugate base? Yes, I can. I'll again eliminate one more H from the same, and I will have PO4 3 minus. For PO4 3 minus, can I have conjugate base? No, I can't have conjugate base because there is no hydrogen atom present in the compound. For HF, can I have the conjugate base? Yes, I can definitely have, because HF, H can be lost and that can convert into fluoride ion, F with minus 1. And this is how you can easily convert any damn compound with respect to its conjugate acid or its conjugate base by keeping a simple theory in mind, simple technique. You can consider simple key that add a proton gives conjugate acid, remove a proton gives conjugate base. So this is how the things are made simple to understand Lorry-Bronsted acid-base theory. This is your Saurin.S.Mehta chemistry channel, and email ID is styrene, styrene 1411@gmail.com for any queries. We'll proceed with Lorry-Bronsted with respect to its limitations, because there are few limitations of Lorry-Bronsted which will be again overcome by new scientist G.M. Lewis. We are still on with acid-base concepts. Prepare well. We'll see you again in the next episode. Till then, goodbye.